This presentation is delivered by the Stanford Center for Professional Development.
And any questions about last time? Because if not, what we're going to do is we're going to finish up this topic of heuristics based on convex optimization for solving non-convex problems. So that's the first thing. We're going to just finish that up. And then we'll move on to another little coherent section of the course, which is basically how to solve absolutely huge problems. So for some of you, I mean, if you've already chosen a field and it's too late, this will be relevant, and you made the mistake of choosing a field where you have to solve huge problems, then it'll be 2 or 3 lectures. These will be for you. For those of you who haven't chosen a field yet, this will give you this will be encouragement to not choose a field where vast and huge problems are required. So that'll be my recommendation. Okay, so let's do difference of convex programming. Let's finish up this stuff. I think we looked at this last time. So this is a topic or method where you write all the objective and the inequality constraint functions. You can do this with equality constraint functions too, but I'm not going to go into it. And what you do is you write them as differences of convex functions, right? So a convex plus a concave function. And then the obvious linearization, convexification I should say, is this. You linearize the concave function. So only the concave portion, that's minus the convex one, is you linearize that. And then this is roughly speaking based on the idea, I mean you can make this precise, but it doesn't need to be, is that the best affine approximation of, the best convex approximation of an affine function is an affine function, right? So, okay, so you do this, and the result, this is now convex, because the convex part you left exactly as it was. And the only thing you've done, that's a constant, is linearize, that's this thing, the concave portion. So, by the way, the way to do this is, for example, it's actually pretty straightforward. The way you would do this for a quadratic, you can work out how that is. If you have a quadratic that's neither convex nor concave, it has split eigenvalues. You split it into the positive part, and that's going to be this thing. And then the negative part, you simply linearize, but you will drop the quadratic, the quadratic term. In that case, linearizing is just dropping the quadratic term. That's only for the concave part. And actually, you'll find out it's quite interesting. If you have a function that's convex, that's difference of convex concave, it'll actually have some negative curvature. And basically, what you're doing is you're just flattening the negative curvature, but you retain exactly all the positive curvature portions. Okay. So an example we'll look at is from the book. It's estimation of a covariance matrix from samples. From samples. So you form the sample mean, and the negative log likelihood function is log det sigma plus trace sigma inverse y. Now I mentioned this last time that the general approach now is to do the following. Is not to estimate sigma, but sigma inverse, that's a one-to-one transformation, so you're perfectly welcome to do that. In which case, this function is convex in sigma inverse, because that's linear, and that's convex, because it's log det sigma inverse. It's log det sigma inverse, so which is convex. So that's the standard method. Now that works provided the constraints you want to impose on sigma are convex in the inverse of the function. Inverse of the covariance matrix. Actually, there's a lot of interesting constraints that are convex in the inverse of a covariance matrix, many. But some are not, and actually we just want to illustrate DCC, or whatever this is, a convex concave procedure or something like that. So we just picked one that's not. So suppose I told you that all the variables are non-negatively correlated. There are no negative correlations. So that's this, and this is not preserved under inversion. So the set of matrices whose inverses are non-negative is not convex. Okay. So that leads us to this problem here, and we have a convex part and we have a concave part. And we're going to linearize the concave part. That's this. I mean, this doesn't matter because it's a constant, and we're going to preserve this convex part. So, and the result here, I think we looked at this last time. I just wanted to make sure I went over this well, is this. And my guess is that this is actually globally optimal. And the reason is actually there's even an exercise in the book that goes over this. It turns out that in some cases, this problem is actually convex in sigma, depending on the final estimated sigma versus the covariance matrix. So that's this. Just to show you how it works. Okay. We'll look at alternating convex optimization. That's our last topic, and we'll look at a couple of examples. So this is another idea that comes up. Lots of times it's discovered periodically, will be discovered periodically in the future by many people in many different areas. Maybe one of you will discover this again sometime in 10 years or even less. That's fine. I mean, actually, there's nothing wrong with discovering it. The only thing wrong with discovering it is imagining that, in fact, you're the first to discover it. I mean, that's the only actual problem here, which there are people who do. Okay. All right. So this works like this. You partition, these aren't actually, sorry, not partitions. I have index subsets here. And you assume that for each of these index subsets, the problem is convex in a subset of variables. So that's sort of that's the picture. Okay? And in fact, we can even, if you like, look at an example just for fun, because that's the only way this really makes any sense. I wonder if you can raise this screen up to about here. That'd be great. Okay. That's good, right there. So let's take a look at that. And actually, let's look at just something extremely simple. Things don't come simpler than that. Okay? And let's imagine the variables are actually, for some reason, A, X, and B. So it's 3 groups of variables. And now I want to know, is that convex in A? What I mean by that, of course, is that X and B are fixed. Is that convex in A? Of course it is. It's affine. It's a norm of an affine function. So it's convex in A. Is it convex in X? Obviously. Is it convex in B? Of course it is. Okay, now let's do pairs. Is it convex in X and B? Yeah. Okay. Is it convex in, A and B? Obviously, right? And the final one is it convex in A and X? And the answer is no. Okay. So this would be a case where there's all sorts of different index sets. So the index sets might be something like this. You might as well give maximal ones, right? So A, B, I guess that's about it, right? If you're going to do that. And you could have X, B. Maybe these are the maximal sets, something like that. So those are the maximal sets, index sets, over which the problem is convex in each set. Okay. Now, the method now goes like this. I mean, it's really kind of dumb. For each of these index sets, it's convex optimization to solve that problem. So you do that, and then you kind of go back and forth and so on and so forth and hope that this works. So actually, let's even look at an example. Suppose I ask you to solve this problem. So here would be the problem. I should remember those sets, actually, A, B, and I think X, B. So in this case, we're asked to minimize this. Note my period. Okay, subject to X in some X. This is convex, right? A in some script A, and B in some script B. Okay, these are all convex sets here. Okay? So obviously non-convex problem. That's clear. It's non-convex. Why? Because of the AX there. Actually, lots of problems come up this way, incidentally. In fact, there's even projects that are literally, directly, this blind deconvolution. I think, is that yours? Yeah, it's yours. Okay, so there's plenty of things that come up looking like this. And so this method would look like this. It would alternate, and it would actually say, first, fix X to the current value, and optimize over A and B. And that's a convex optimization problem. That would update A and B. Then it says fix A and B and optimize over X and B. Okay? So notice that B is being optimized actually every step. I mean, this is not a big deal, but it's just to illustrate kind of how this works. So that's the picture. Let's see, what can you say about this? Nothing. I mean, that holds for this entire lecture. But I don't know, you could say trivial, stupid things, but after a while they get kind of, you realize, like, why bother? If there's theorists around, I don't know. It's stupid. Look, obviously, when you do this, every time you do it, the objective goes down. So amazing, isn't it? The objective actually, it's a number that goes down, therefore it converges, if it's bounded below. So, I don't know. And then so what? So, okay. I don't know. That's better than nothing or whatever, but it's so obvious that I don't even see the point of stating it. Okay. So, a special case is actually when you partition the problem into two variables, and you just alternate. By the way, there's lots of variations on this. That's the nice part, is because it's an algorithm that often works but need not. It means actually that this holds for this whole lecture on non-convex optimization, is there's lots of room for personal expression, which is not the case basically for convex optimization, because a method that solves a convex problem doesn't badly is just called a non-method, right? And any two methods if they disagree on the answer, one of them is wrong. One of them is a not acceptable method, right? Well, for a non-convex optimization, who knows? It's very nice, Maybe your method works better on one problem instance, mine on another. So it's very nice. You get room for personal expression. I can mention some of the variations that you can do for this. One is actually to not optimize all the way, but to take a fractional step in between. So that's an option. Doesn't sound like it makes sense, but actually that can actually make these things work better and so on and so forth. But just remember, that's alchemy. That's just like, who knows? It's just go ahead and try it and see what happens on your problem. So that would be, in other words, you would optimize, for example, over A and B, and not step A and B all the way there, but step them some fraction halfway. And okay, all right. So this is alternating convex optimization. Here's a recent and interesting application of this is non-negative matrix factorization. If you don't know about this, you probably should, although the people popularizing it are making way too big a deal out of it, but that's okay. They're welcome to do that, because it is really cool. Here it is. It's sort of like, you might call it a signed singular value decomposition. So basically, I give you a matrix. I want to explain it somehow as a low rank matrix, as an outer product, something like this. And you should imagine that K is small here. So K, you might want to approximate a matrix A as an outer product of I guess in this case, m by 5 and then 5 by m. So you'd have sort of like 5 factors or something. Now, without this is completely solved. It's just the SVD. You take the SVD and you truncate the SVD expansion, and you get the answer. Let's see. Oh, by the way, it's even. There's lots of. It's not unique here, and that's completely obvious because I can put a positive matrix, K by K inside here, and I get the same. I get the same. I get a different factorization that yields exactly the same objective value. So it's not unique, but that doesn't really matter. Let's see, a couple of cases we can solve. We can do K equals 1. So you can actually approximate a matrix in Frobenius norm. Well, any norm doesn't matter. Frobenius norm or spectral norm with a outer product, which is restricted to be positive, and that goes in 2 steps. You first take the positive part of A, that's the first thing you do, and the next thing you do is you take the singular value decomposition of that. Now, it turns out there's something called Perron-Frobenius theory that says that the singular values of a positive matrix, singular vectors of a positive matrix, the first ones associated with sigma 1, which is what would come up in the rank 1 approximation, those can be chosen to be positive. Okay, so that's one case where you can do it. Okay, now on the other hand, come on, it's just this thing. You look at this and you realize, wow, it's certainly convex in X if Y is fixed, and it's convex in Y if X is fixed. And so you can simply alternate over these, and you can say a few things. I think in one of these variables it's actually separable. I forget which one. I don't think it matters much. Maybe in the columns of Y or doesn't matter. It's separable. Actually, the separable is not that exciting unless you're going to run on many machines, unless you're going to do like an MPI or something like that. Because as we've discussed several times, If a problem is separable, it just means the computation time grows linearly with the problem size. But that's the case even if there's light coupling by these sparse methods. So, okay, this is non-negative matrix factorization. And here's an example with 50 by 50, a 50 by 50 matrix, and we want to show it, we want to approximate it as a rank 5 matrix. And then here it is starting from, say, 5 starting points, and you can see it's going down like this, and will converge. It need not converge to the, in fact, it's unlikely to converge even to the same, might converge in this case to the same one, but there's no guarantee and all that sort of stuff. So all of these methods, these non-convex methods, they're extremely useful. So the fact that no one, if you're doing the Netflix challenge or something like that, and this method works, I don't think you're going to sit around and complain and lose sleep over the fact that you're using a method that you can't, prove always gets the global minimum. So there's lots. You have to remember there's lots of cases where this stuff is fine. It is actually, it works perfectly well. Right? If you don't get the optimal trajectory for your robot, as long as you reliably get a really good one, that's fine. There's other cases where you can be much less, you can't be as casual about not finding the global solution or something, but this one. Yeah?
In this problem instance, did you create A to be the product of 2 positive matrices?
No, we didn't. Okay. I think it's just random. All the source code's online. You can look at it.
If you did this, would you get the answer usually, or?
I think you said it just right. Yeah. The obvious thing to do here is to make A, generate A as XY and see if you get back XY. By the way, you won't get XY, right? Because there's a what do you call it? It's not unique. But you'll get something. You should get this. They should have the same ranges or whatever. They should be unique modulo this transformation. You should get the right X and Y back. Yeah, I think what happens in that case is you often get back. So I think you said it exactly right. You usually get back what you were looking for. So it's a heuristic. You do not have to get it back. For one thing, it depends on where you start from. So, yeah. But these things work pretty well often. Okay, so that finishes up this. I should say this was sort of it was out of order for the class. It was out of order because that was just a whole lecture on non-convex methods, kind of stuck in the middle of the class. It kind of logically goes at the end, but I thought we'd switch it around for the benefit of those doing projects that are involve non-convex problems. Yeah?
So SVD solves like a non-convex problem.
It does, that's right.
So are there extensions of SVD that are guaranteed to find a global optimum that solve like similar non-convex problems? Good,
that's a great question. So a good question is, what are the problems that aren't convex that you can actually solve? And now we're back, by the way, now that lecture's over, we're back. Solve now, once again. We just went over the right bracket, and the scope solve now means solve globally. Doesn't mean this kind of, maybe possibly get a local solution sometimes, which is what it meant in the last lecture. So we're back to the global definition, because that block just finished. And then let's answer your question. So the question is, clearly there are non-convex problems we can solve. One is things involving what's the best rank 3 approximation of this matrix? We do that by truncated SVD. That is plenty non-convex. Okay. And there's actually so the question is, what are the others? And there's a handful of others. So there's we can solve any problem that involves 2 quadratics, convex or not. And that's just, it's actually not obvious. And then you can involve some weird things like some things involving quartics, but it depends on the dimensions. And these are just by sort of accidents of algebraic geometry. But we're not going to talk about it. But the point is, I guess my opinion is there's just a handful of problems that are non-convex that you can actually solve. And I mean in the strong form of solve as in get the solution, right? So if that's what you mean by solve, there's just a handful. SVD is one, and you're going to find plenty of others. But yeah.
So if you have a convex concave problem,
Mm-hmm.
why can't you maybe approximate one of them with one quadratic, approximate the other one with another quadratic, and then iteratively use that to solve that
That doesn't solve the problem. What you can do is you can minimize any quadratic function, convex or not, subject to any single quadratic inequality, convex or not. Okay? By the way, you know some examples of that. Like, how do you minimize x transpose ax subject to x transpose x equals 1? Answer, minimum eigenvector. Okay, and that's a non-convex problem if A is not positive semi-definite. If A is positive semi-definite. Well, actually, with the constraint there, x transpose x equals 1, it's non-convex there. So, yeah, so there's a handful of these, but not a whole lot. But they're good to know about. I mean, so that's actually in the appendix of the book if you want to read that. It's an advanced topic, and that also is something which is discovered. That's actually something deep, unlike difference of convex programming, which is basically just an obvious kind of trick. That's actually deep, and you can actually say, I mean, that's a strong statement. And yeah, people periodically, about once every 10 years, rediscover that in different fields. So it's got lots of different names, like Parrott's theorem. You look in the appendix because we listed some of the things there. So, okay. But if you have two quadratics, you can't do it. Although there are some weird isolated cases where you can solve it with two quadratic constraints. So it's weird. And then there's weird things where there's like quartics, and so there's just a handful of random things that people who study these things would know. And by the way, in almost all of those cases, not in the eigenvalue case, but in some of these cases, it turns out that these non-convex problems you can solve are basically because you form a convex relaxation, solve that, and then you prove separately that the relaxation actually can always be rounded to it's always tied or something like that. So that's how those work. And those always involve real stuff. If you look in that appendix, it's not simple. So, okay. So that finishes up that. Like I said, we had a right bracket, so that means we're back to convex optimization again. And we're going to start another chunk of the class. It's another coherent chunk of the class, and it's basically on how to solve extremely large problems. So basically, as big as you want. If you can store the data, basically we can solve the problem with a memory that's basically on the order of the size of the data. Number one. And with that computation, it's completely linear, right? So when you get to problems that are million variables, 10 million and more, n squared, the 2 doesn't do the trick, basically, either in storage or anything else. So I mean, nothing even remotely close to that. You can handle an n to the 1.1 or something like that, or 1.2. Beyond that, forget it. So we're going to look at these methods. They're actually extremely good and extremely cool, and I think just any educated person should know these things anyway. Even if you've made the wise choice to go into a field where the number of variables is and will remain for the foreseeable future under 1,000 or 10,000. But if you're in a field where things are going to grow, this is going to be part of your future. So okay, so conjugate gradient method. By the way, how many people have seen this somewhere? Okay. Oh, good. Okay, where? Some ICME thing or? Okay, so you'll know everything.
CS205.
CS205? Okay. Oh, okay, great. That was...
Mathematical methods for vision, robotics, and graphics.
Oh, okay, good. Okay, good, great. Okay, so a bunch of you have seen it. You probably have seen more of it than I have. So for you, you can just sit back and, I don't know, relax or something. So for the rest of you, it's great stuff to see. Okay, so first let me start with just sort of the really big picture about solving linear equations. Now, actually, I'm sure all of you know the following. I've said it many times, but it's important enough I'll say it again. If you profile certainly most convex optimization methods, if you profile them and ask while it's running, what is it doing? It's solving linear equations. That's it. And there's a bunch of other stuff, but it just doesn't even show up in profiling, like little line searches and evaluating logs. Zero. Okay. What really matters is computing the steps, and that's solving linear equations. So, okay. So, by the way, it's true for a lot of problems. It's just solving linear equations. So let's talk about at the very big picture. How do you solve ax equals b? Okay. So it's kind of a crude classification. It's actually wrong because there's the boundaries between them are gray. But in fact, it's helpful to classify these into three huge classes, and here they are. One is dense direct. These are factor solve methods. We covered this in 364A. You've probably seen it other places. This is basically, I mean, the software involved there is almost universally LAPACK and BLAS. That's, I mean, if you use MATLAB, that's what you're using. Actually, if you use anything reasonable, that's what you're using. So these are factor solve methods. You factorize A into a product of matrices, each of which is easily solved, and then you do a back and forward substitution or something like that. Now, here are the high-level attributes of these methods. You can take an entire class on just this, right? No problem. It's like CS 237 or something like that. And that would go through all the horrible details of how do you do the factorizations, what are the round-off error implications, and all that kind of stuff. But at the highest level, here's what you need to know about these methods. The runtime actually depends only on size. That's not completely true, except for positive definite systems, in which case it is true. So for indefinite systems, you do dynamic pivoting. So which means that there actually are conditionals in the code. You look for a new thing and you reallocate. And unless you've allocated memory correctly ahead of time, I guess in this case that wouldn't happen. Sorry, scratch that. That's coming up. So there are conditionals, and that means that actually solving AX equals B for a general matrix A actually is not independent of the data. If I give you one A or another A, it can actually take slightly different amounts of time. Actually, it's absolutely second order. So you won't notice it, but it's not deterministic. If A is positive definite, it is absolutely deterministic because it's a Cholesky factorization. You do not pivot in a Cholesky factorization. Actually a compiler will unroll the loops, and it's just, it's whatever it is, n cubed over 3 operations, all pipeline, and it just shoots right through. And there's it can never be different. It will be repeatable, down to the microsecond or lower. Okay, so that's this. Well, there's a few other things that happen. Of course, it can fail. I mean, it can throw an exception if you pass it as singular A. So, but roughly speaking, other than that, it's deterministic. Has nothing to do with the data, except of course, when you get to the boundary of where A is singular. It doesn't have to do with the structure of A. If you toss in a Toeplitz A or a sparse A or banded A, this thing doesn't care. Okay, and this will work well for n up to a few thousand, I mean immediately. And you can do the arithmetic to find out it has to do with how much will fit in your RAM and stuff like that. So this will work up to a couple thousand. If you want to use a bunch of your friends' machines and use MPI or something, you can probably go bigger than that. But that's, you can just, this will scale up to much bigger problems, but not on a laptop or a little machine or something like that. Okay. So the advantage of these is that it's very nice. It's just technology. This is just A\B at the highest level, just done, right? Extremely reliable. When it fails generally because you gave it a stupid problem to solve. That is to say, A was near singular for some practical purpose. Okay. Okay. Now this is the first level. The next huge group is called sparse direct. So these work like direct means you still are factoring A, but this time you're taking into account sparsity in A. And these, sometimes there are well-known named structures, like A could be banded. That's a case where it's named, or it could be just a sparsity pattern in the sense that there's just lots and lots of zeros all around and so on. Okay, so those are sort of different cases, but they're both, I would call them both sparse. I'd put them in this part. Now here, the runtime is going to depend on the size. Of course, that's always the case. The sparsity pattern, and it's almost independent of the data. It's actually a little bit less independent of the data than it is here. And the reason is in the general, unless it's a Cholesky factorization, you're actually doing dynamic pivoting. And in this case, dynamic pivoting has fill-in effects. And so you may even end up, if you end up calling malloc or something in the middle of one of these things, you're going to be sorry. So in fact, the way these typically work is you'll actually you'll actually allocate, before you even go in, you'll allocate a block of memory, hopefully big enough to contain all the fill-in that is going to happen, because as you're dynamically going through it, you're generating fill-in because you didn't like the pivot that you would have taken or something like that. Okay? So that's what this is. And this depends on the sparsity pattern. This will take you up to 10 to the, generally 10 to the 4 pretty easily. 10 to the 5, now if it's special, like if it's banded or block banded or has some, arrow structure or something like that, you can easily take this up to 1 million. I mean, if it's extreme, if the sparsity pattern is, well, let's say it's banded, you can go to 1 million like that. So my laptop will easily go up to 1 million. No problem. Just none. You can just work out it. You just figure out how much DRAM it takes. It's just totally straightforward. By the way, this is described at least at a very high level, more than I'm going to say about it here. This is in the appendix of the book on convex optimization. Of course, there's entire books on these subjects too, many, and a lot of them are really good. So it depends if you want that much detail, but it's all there. Now, the interesting thing about these is you could argue that these are completely non-heuristic. They always work. If you type in a random matrix, full, dense, before you hit A\B, I'll be able to tell you how long it's going to take. I mean, if I know a little bit about your machine. And I will not be wrong. I absolutely will not be wrong, because I know what it is. Ahead of time, we can guarantee it, all that kind of stuff. I can embed it in the real-time code, and we just know how long it's going to take, end of story. These actually are semi-heuristic, and you have to be a little bit careful about this. What that means is the following. After a while, you get used to these to sparsity being handled. There is some heuristic in the sparsity stuff, and the heuristic comes into the ordering. So how you pick the permutation to do your stuff. That's a heuristic. And that's actually a whole field which is very interesting. But there is a heuristic, and it's this. So when you type in your problem and you have 100,000 variables in AX equals B, and you type A\B, I mean, this is if you're doing MATLAB, but remember, they didn't write any of the numerics, right? It's all doing stuff that's written in C and stuff like that. In that case, probably UMF packer. I'm not quite sure, but I guess that's what it's doing. What will happen is this: there is a moment where of tension, and it's either going to take like 2 seconds or 12 hours or something like that. It's very likely to take 2 seconds, right? But that just depends on your sparsity patterning and the ordering method you're using. So, okay. And now we get to the third class. Oh, and by the way, these are not, I'll say a little bit about the boundaries are gray. Any sparse direct method does this. When it gets near the end, and it's got a little block at the end it's working on, and it's all dense, it usually when you get down to like 1,000 by 1,000, it just says, screw it, I'm going dense. Even if there's lots of zeros in it, it just goes LAPACK at that point. Just blast LAPACK. So a real sparse matrix solver, if the fill-in gets big enough, it just says done. Blast LAPACK and does it. So that's why the boundary's not exact here. Now we get to the third class, and it's the one we're going to study now. It's iterative methods, also called indirect. If you do this is basically how all scientific computing does, so large scale, your example of that. It's PDE solvers, it's anything large scale. Typically anything with 1 million variables and more, you're talking iterative. Unless it's very structured, like banded or something, you're talking iterative. Now, all of scientific computing, so on. All right, now these methods, and notice that we're losing reliability every time we jump up one. The first one is like, it just always works. I didn't even have to hear your data, and I can predict exactly how many milliseconds it's going to work. It is 100% reliable unless you throw in something stupid data at it. Then you get to sparse. I can say, it probably is going to work. It depends. Depends on your data. Depends on the matrices, and it also depends on the ability of the heuristic for choosing the ordering. Whether that's going to actually give you a good low fill-in factorization. But after that, after that's going to work once you know the fill-in story. Here, the runtime actually depends on the data, and the required accuracy. So the other two methods are basically producing very accurate solutions. In infinite precision, they're producing exactly accurate solutions. That's a real issue, which I'm not covering, but that's it. Here, these things are tough. These require tuning. Preconditioning, that's something we'll talk about. And I'll say a little bit about that. So these are less reliable. They need babysitting. These are not just backslash type things where you don't embed these in there. You have to tune it. Now, on the other and you'd say, well, that's a pity. Of course it's a pity. I mean, imagine what a pain in the ass it would be if every time you type A/B, you actually had to tune or tweak like 6 parameters to make it work. So welcome to the world of super large scale problems. Is tweaking, that kind of stuff. Preconditioning, we'll get into that. So you could say it many ways. There's lots of opportunity for personal expression here. A lot of this is not fun too, and therefore it often falls to graduate students to do. Just to warn you. Doesn't mean anything to me, but trust me, this is the kind of thing ideal for graduate students to do. Okay, and you can complain about this all you like, but the point is, if you're solving a problem with 1 million or 10 million variables, and something's actually coming out, you hardly have the right to say, God, it's a pain in the ass that poor grad student had to work for 3 months on the preconditioner, and the solutions aren't that accurate. You'd say, hey, look, you were the one who decided to solve a 10 million variable problem. You can't. There's not much you can say after that. Okay, so this is the third method. By the way, the boundaries between them are actually they're a bit gray. So for example, people will often use a few steps of an indirect method or iterative method, actually after one of these. That's called iterative refinement. People will also use a preconditioner. We'll get to that. Is a preconditioner, which is in fact based on an incomplete factorization or something like that. And then, so at that point, who knows what these things are? So, but it's useful to think of these 3 huge classes of methods for solving linear equations. That's very useful. Okay, so now we'll get into one, most famous one. Well, a lot of them are the same after a while. You get it. So we're going to look at symmetric positive definite linear systems because actually mostly that's what we're interested in. We solve either Newton equations, Newton systems, which is H inverse G minus H inverse G. Or even if we're solving with equality constraints, we have a big, an A transpose A 0, a big KKT system, which is indefinite. But if you do block elimination, you end up solving something that looks like, A H inverse A transpose or something like that. So a lot of it comes down to solving this. Okay, so this comes up, for example, in Newton, in a Newton step is that. It's least squares equations, regularized least squares. If you minimize just a convex quadratic function, and of course this is also solving an elliptic PDE like a Poisson equation if you discretize. So that's what you end up doing. So, okay. As another example, it's sort of just analysis of a resistor circuit. So this comes up also in circuit stuff. Here that you'd have a conductance matrix, and an I is a given source current, and you want to calculate all the node potentials or whatever. By the way, same thing comes up in analysis of reversible Markov chains. That would be another one that I didn't put here, but it would be the same thing. Actually, it's related to this. So if I give you a reversible Markov chain or something like that, and I say if I start the thing here at this state, and I want to know what's the probability that it hits this state before that one or something, you're basically solving a problem like that as well. So, or if you want to calculate like hitting times and all these, it's the same sort of thing. Okay, so now we get to CG. Actually, there's a bit of a confusion over the method. It's sometimes called conjugate gradient and sometimes conjugate gradients with the S there, and it's kind of, I don't know. I may switch between them, and then I think it also depends if your first exposure to this is if it's I think one is the British style and one's the non-British style. Anyway, but just to warn you, you're going to see S, sometimes not. Okay, so it was as far as anyone knows, it was first proposed in 1952. By Hestenes and Stiefel, and it was proposed as a direct method. And now here's instead of getting into the details of the method, in fact, we won't get to the details of the method until well actually, the details of the method are actually irrelevant. That's probably not how you guys learned it, but we'll get to that later. There's actually many actual methods that will generate the same sequence of points. But we'll get to that later. Here's what it does. Here's high-level attributes are this. It solves ax equals b, where that's symmetric positive definite. Now, in theory, if you were to do exact arithmetic, it takes n iterations. That's the dimension. Each iteration requires a few inner products in Rn. That's fine. And it requires a matrix vector multiply. You have to implement a method that, given z, will compute az. So that's what you have to do. That's basically what you have to do. Okay. Now, if you work out that arithmetic, if A is dense, then no problem. You call AZ. And if A is dense, you're multiplying n by n matrix by vector. That's n squared flops. And congratulations, you run CG. It takes n steps. Each step is order n squared, and you're back to n cubed. Actually, what you have now is an order n cubed solver that is much less reliable than the standard ones, and actually much less slower, because you're using blast level 1 or 2, or I guess that's blast level 2, because you're using matrix vector multiply, whereas the real method for solving it would use blast level 3 and things like that, which would be block. And it would use, that would be optimal. Okay, so there's absolutely no reason to use a CG type method. I guess, to tell you the truth, CG is really a particular method. And honestly, this really should be called Krylov subspace methods. I should even change the slide. I feel so weird, because it's really a specific method, but they're all kind of lumped together. Okay. All right. Now, if ever matrix vector multiply is cheaper than n squared, you can do better. Okay. So here's an example. If A is sparse, multiplying z by az is fast, because you only multiply by the non-zeros. Now, if it's sparse and not absolutely huge, you're probably better off using a sparse method, like a sparse direct method. Maybe, okay? But let's see, someone give me an example of a matrix, n by n, you can multiply a vector by fast. Fast means less than n squared, but which is full, not sparse. What's an example? I guarantee all of you have seen these.
Like an outer product matrix.
Perfect. Actually, that's perfect. Yeah. So a matrix that's like, diagonal plus low rank. Yeah. Diagonal plus low rank. I mean, you have to know it, represent it that way. Yeah. Perfect example. Diagonal plus low rank is clearly full. I mean, generally, it's going to be dense, and yet you can multiply. If you know that method, you can multiply real fast. Anything else? This is classic. Undergrad EE. FFT. So I think, and the right way to say it, let's say it right. A would be the DFT matrix. It's n by n, and you'd carry out the multiplication using the FFT algorithm. And that would be n log n as opposed to n squared. So that's an example. There's a whole bunch of others. We'll probably mention some of them. Now we get to the bad news about CG, and this was recognized already in the 50s. It works really badly with round-off error. So some methods, the round-off error doesn't really matter, or it has an effect, but the errors don't build up as you go. Others, it's just a disaster. This is just almost universally a disaster. I mean, except for the baby examples I'll show with like 10 variables, where CG would be highly, 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 highly inappropriate to use. So otherwise, it's almost universally it works terribly. So that's the out of the box. We're going to see some tricks that will make it work reasonably. Okay, but here's a very important attribute of this method, and it's this. Depending on A, B, some luck, the graduate student that put it all together. Well, no, that's then what happens is kind of cool. In a very small number of iterations, you can get a rough approximation of the solution quickly. That's a very different thing. If you go back, let's solve a circuit. I have a circuit with 1 million nodes. I pump in some currents. This is one step in running SPICE, let's say. So one time step. I pump in some currents, and all I want to know is what are the potentials there. If I use a sparse direct method, and I send an interrupt signal to it, and I just say, nope, sorry, give me the voltages. It's like, what do you mean? It's not even, I mean, it says I haven't even done I haven't finished factorizing it. So I can't give you anything, right? So, but CG, if you run CG on this, it's just doing iterations, and it's like, well, I was going to do 1,000,000 iterations. I've only done 300, but sure, okay, no problem. Here's V. So these are, some people call these like anytime algorithms. That's one name for this, which is kind of dumb. It means you can interrupt at any time and ask, well, the contract is if you interrupt it ahead of time, before it declares that it's finished, you can hardly complain about what it returns. But it returns like an approximation. And in fact, we'll see that for CG, and you'll even see why in this case because you can analyze it. You're actually going to get a shockingly good, and in fact, there's whole fields that are based on this which are actually quite funny. If you talk to people who do like image restoration or they work in astronomy or something like that, they're huge. And so they say, what do you use? CG. And you go, how do you actually do that? And they go, yeah, we run like 10 steps. And then you go, oh, that's your method? And you go, yeah. And I've actually had a conversation with a person who said, yeah, we run 10 steps of CG. It was like for geophysics or something like that. So they do 10 steps of CG. And I said, well, why not 20? And they go, oh, because each step takes like, an hour. These are, 3D, big, giant, huge things, right? Okay, so each step, and I said, well, what happens if you run it 20 steps? They say, oh, then it starts looking bad. So basically, it's already in 10 steps. At 10 steps, this is for a problem with like, 10 to the 9 variables or something like that, right? In 10 steps, you've already gotten some vague outline of like what you're looking for. But the round off is already killing you after about 20 steps or something like that. And I'm like, and you guys are cool with that? And they're like, oh yeah, no problem, that's fine. They're like, so that's their prescription, which is run CG until you run out of time, or the round off has built up and the results start looking worse. I mean, perfectly good method. I should say, here's the joke. I'll tell you something. So you will actually, in your homework, when we figure it out and assign it, you'll run some CG things. And in fact, there's a MATLAB PCG thing which you'll use, and you'll be very thankful for it, even though it's like a 5-line method. And it, in fact, when it returns, if you say run CG 50 steps, what it returns by default is actually not the iteration after 50 steps, but in fact, the iteration between 1 and 50 that had the best residual. And this is not for the reason that you see in a subgradient method where it's not a descent method, where ahead of time this is not a descent method. You'll see this is supposed to be a descent method. It's only not a descent method because of round off things and things behaving poorly. Okay. All right. So let's look at the, how this works. Well, the solution, we'll call it X star. That's A inverse B. And because A is positive definite, there's a very useful thing when you're solving AX equals B where A is positive definite. A very good way to think of it is this. You are actually minimizing a convex quadratic function. And that fits actually in lots of applications. For example, if you're solving AX equals B and someone says, why are you solving that? You say, I'm doing Newton's method. Someone says, explain to me Newton's method. Then you really realize, in fact, what you're really doing is you're minimizing this. Because Newton's method goes like this. Someone says, what's Newton's method? And you say, well, I'm minimizing this weird function. I have a current estimate of x, and I go to the function, and I get from it a convex quadratic approximation, and I'm minimizing that. So in fact, this connection is not it's not abstract. It comes up in the applications. Okay. Now the gradient of this function is ax minus b, but this is also, that's the residual. So residual and gradient of this function over here is going to be, they're kind of the same. Okay. Now, if you take f star is f of x star, that's this, I guess that's this thing plugged into that, and I forget what it is, but there's like an A inverse there or something like that. You get an you get a B it's minus B transpose A inverse. Anyway, it doesn't matter. But if you take f of x minus f star, here's what you get. That is, here's f of x here, and then minus x star, and you can rewrite that this way. And so it's actually x minus x star this is the square of, and this sub symbol here means it's the A. People call that the A norm. So that's the A norm, and it means it means A is positive definite. This is sort of the distance in that metric. So F minus F star is half the squared A norm of the error. Yeah.
I just want to know between the first and second step, where did the B's go?
What's that?
The B transpose X terms.
Yeah. You mean
They just
here?
no.
Here?
When we are calculating Fx minus F star,
Yeah.
since X and X star are likely to be different,
Yeah.
B transpose X terms.
You mean these don't cancel away? Yeah. Is that what you're saying?
Yes.
Yeah. No, I don't think. I mean, unless you're really good, I don't think you can go from this line to this one by just looking at it. There's a whole bunch of lines out there commented out. No, I mean, right? Yeah, look, but X star is this thing. So X star itself has a bunch of B's in it. So when I throw it, this term here, when it all expands out, it's going to have a giant pile of B's as well.
I mean, B transpose X star is X transpose AX, or like.
Hey, that's a good point.
Yeah.
So let me respond to your question by saying these are not meant to be self-evident. There are many commented lines out, and in fact, they may or may not be correct. I'm going for like 80, I'd go 85% on the reliability, maybe 90, but I think they're right.
You're assuming A is positive definite?
I am. Yeah, in fact, A is positive definite until I tell you otherwise. Okay, so. Yeah, I mean, otherwise, a lot of this doesn't make any sense at all. Okay. Okay. Now, a relative measure would be something like this. F of x minus f star divided by f of 0 minus f star. And that would be something like that. That's tau. And it's actually the fraction of maximum possible reduction in f compared to x equals 0. And actually, these things are very interesting. Here would be one. In a Newton method, this would have a beautiful interpretation. It makes perfect sense. So in a Newton method, it would go like this. You have a convex function. You're at a point. You form a quadratic approximation of that function, and then that goes down. And in fact, if you were to find the minimizer of that and take that step, that's the Newton step. And in fact, that height difference is lambda squared over 2. That's the Newton decrement, if you remember that. So that tells you sort of if the quadratic approximation is right, it predicts how much you're going to go down. If tau is a half, it says that you don't have the Newton direction, but you have a direction good enough that you will achieve 1/2 of the reduction you would have gotten had you gotten the exact Newton step. So if you could actually calculate tau, which sadly you cannot as you run these methods, but if you could, it would be very useful because it would basically, there's no reason you don't really care about the Newton direction. In fact, what you really care about is a direction that's going to get you a good enough decrease, right? And something like if tau is a half, you could jump to the next. You could quit and use that method, use that direction. Okay, so just say a little bit about the residual. By the way, I mean some of these are not too obscure. I mean, so some of these multi-line things. One line should follow from the next, but not all of them. I mean, without some paper and stuff like that. Okay, so this is the residual. It's the negative gradient, and you can write it this way. But in terms of this residual, you have f minus f star. Turns out to be 1/2 of the residual norm, but in the A inverse norm. Okay, so in fact, in all these methods you're going to see, a lot of things are going to be very naturally stated in terms of the A or A inverse norm. Now, sadly, this is generally not the norm you're interested in the residual or something. It can be in some applications. Generally, you're interested in the actual residual norm, for example, and that's one of the things that's that you're not going to have easy access to. But a very commonly used measure of the relative accuracy is the residual norm divided by B. So that's very common. By the way, B is the residual norm if you guess x equals 0, right? Because then ax minus b is minus b or whatever. And so basically, if this number is bigger than 1, it means that's not a really good estimate of the solution of ax equals b, because in fact you are outperformed by a function which is 6 characters that returns the vector 0, which is that's not a good place to be. Anyway, so that's not impressive performance. So this is usually how this, and it scales it with the problem size and things like that. Now you can show that tau is less than the condition number of a times eta squared. And we'll see that well, I mean, here eta is easy to, as the algorithm runs, you have x, and you'll see part of the algorithm is you're going to calculate the residual at each step. You're going to calculate ax minus b. Fine, you can take the norm of that. That's easy. You know b, you can take the norm of b. So tau you're going to get, eta you're going to get very easily, and you'd get something like that. If A were well conditioned, this might be useful. So this is really, and this is maybe not so useful in practice, but it basically says that tau, which is arguably what you're really interested in, if eta is small, then tau is going to be small too, something like that. Of course, you don't know the condition number of A generally, so this is not that useful. Okay, now we get to the basic idea. So the basic idea is one of it has to do with Krylov subspace. Actually, who knows how to pronounce it in Russian? So, because that's not how you pronounce it in Russian. Just to let you know. But it's been around. I figure it's been around for a long time. We've been using it since 1952. So now it's a Krylov subspace. It no longer refers to this guy's name. Okay. So, and that means we have license to mispronounce it. So okay. So this comes up in a lot of places. A Krylov subspace is this. It's the span of B, AB, up to AK minus 1B. If you've taken like a class on linear systems or something like that, it's also called a controllability subspace. And it's got other names in other fields, and I forget what they are. But it comes up in a bunch of other fields. That's called a Krylov subspace. And here's the cool part about it. It can be written this way. It is the set of vectors that can be represented as a polynomial of A times your vector B, okay, where that polynomial has degree less than k. So that's the same thing. So you're basically you take polynomial of A, any polynomial of A up to a certain degree, and multiply it by B. Okay, that's very important. It's totally obvious because a linear combination of these is a linear combination of powers of A then multiplied by B. Okay. So the Krylov sequence, x1, x2, and so on, is defined this way. It's the minimum of this f of x, that's that quadratic function, over the kth Krylov subspace. So that's called the Krylov sequence for a given A and B, right? So for example, the x1 is something like this. It's along the only direction you search on is B, and so you adjust the coefficient in front of B so that you get alpha B minimizes norm A x minus B square. The quadratic form. Okay, so that's what you'd minimize that along there, and you get some multiple. So now there's many methods to compute the Krylov sequence. Many. But the CG algorithm is the most famous one. But there's others. So, and it's actually worth not focusing on CG and actually focusing on the meaning of the Krylov subspace. Okay. So that's the idea. All right. And now let's look at some properties. Well, your function goes down. That's because you're minimizing a convex quadratic function over a bigger subspace. If I minimize a function over a bigger set, let alone subspace, the optimal function value can only go down, can't go up. I mean, it could stay the same, I guess. Okay. Now, if you go here all the way to n, you get x star. Okay? So, and that's actually the case even when the Krylov subspace does not fill out all of Rn. So it's a fact. That comes from the Cayley-Hamilton theorem that the the solution of ax equals b is in the span of Kn, the Krylov subspace. Let's give an example. Someone give me an example of when would a Krylov subspace have shockingly small, not be, when you keep running them, you get the dimension doesn't grow. What would be a good example? Oh, here's one. How about this one? How about, well, here's an extreme would be b equals 0. So what are the Krylov subspaces when b is 0? They're all just the point 0. They're singletons. They have the only element is 0. Okay, those are the Krylovs. They are subspaces, right? Everything's cool. And if you want to minimize, if you want to minimize that, this sequence is just 0, 0, 0, 0. This is when b equals 0. But here's the good news. The first one is a hit because the solution of ax equals 0 is x equals 0. So it's okay. A more extreme example would be something like this. What if b were an eigenvector of a? Then what does the Krylov subspace look like? Well, it's just the first thing. You get b, then you get a multiple. So actually all the k's are the same after k1. So k1 is k2. But again, no problem. Because then it says, after the first point in the Krylov sequence actually solves it. Because it turns out in that case, if ax equals b and b is an eigenvector, then in fact, x equals a inverse b, which is actually along the direction of b. But we'll get to that. So, but that's obvious anyway. Okay? So, okay. All right, now this, the kth Krylov sequence is a particular polynomial. That's a polynomial of degree less than k times b. Now, so far, everything's actually fairly obvious. And now we get to the cool part. And it's not obvious. It's not obvious. And here it is. It turns out that to generate xk plus 1, you can generate it from the previous two, like this. And then these are alpha k. In fact, it's just a linear recursion. These are numbers that are going to come up. Their particular values are going to come up. This is not obvious at all. And this relies on A being positive definite. That's it. So in general, if I just said that's the Krylov, here's the Krylov subspace here, and I asked you to calculate xk plus 1, you would actually have to look back at all, I mean just in general, and in fact if A is not symmetric, you will actually have to look back over all of them. Okay? What that means is the effort to produce the next point in the Krylov subspace is actually not going to grow with k.
So are you just taking the residual and getting the best approximation in the last?
No, you're not.
You're not.
You will see what it is.
Okay.
Yeah, it's not quite that. You'll see. So, it's these things are not totally obvious, and we'll get to what they are. So that's it. So if you want to know like why is this interesting and all that sort of stuff, it all comes down to this one statement. That's where the non-triviality is. Okay. So, okay. And just, I think I mentioned this already, but the Cayley-Hamilton theorem says that if you form the characteristic polynomial like this of the matrix, then it says you can write, then it says that that's 0, and therefore we'll take A to be non-singular, positive definite. So you take all these terms, not that last one, and you pull an A out, for example, on the left. And then you put this on the other side, and you get this. You get an explicit formula. And this, I think, if you took 263, we saw this, and I probably mentioned it. In fact, my forward reference was to this moment, because I said there are, most of the things I would say in a class like that, like, we'll get to that later, we never do. I don't know if you noticed that. But in this case, we actually did, if you stuck it out this long. So, okay. So this says that the inverse of a matrix actually is a linear combination of powers of the matrix up to n. Okay? And in particular, it says that A inverse B is a polynomial of degree less than n of A times B. So it's in the nth subspace or whatever like that. Okay? So that's That's the idea. So even if the Krylov subspace, by the way, doesn't fill out all of Rn, which of course in general it does. If you pick a random B and a random A or whatever, it's going to fill out everything. Okay, so that's it. Okay, so now we're going to look at the spectral analysis of the Krylov sequence. So what we'll do is this. We'll take A and we will write its eigenexpansion or spectral decomposition. And lambda is going to be this diagonal matrix with the eigenvalues. And we'll define, y is Q transpose X. That's Y expanded in the Q basis. B bar is going to be the same thing. Y star is going to be that. And basically this means that the whole problem has now reduced to everything's diagonal. Now, this is not a method. This is a method for understanding it, just so you know. So it says this. F of X is F bar of Y bar. And I just plug in this thing. That's going to be my, this is going to be my Y, and that's Y transpose. And so you end up with this. But now this thing is completely separable, and it looks like that. Okay? So, yeah. I mean, this is a bit silly, right? It says that if you want to solve Ax equals B, and someone were kind enough to provide the eigen system, you could solve Ax equals B very well, because you'd transform it, it would convert to a diagonal system, and solving Ax equals B where A is diagonal, that's easy. That's no problem. And so you'd be asked to minimize this, and that what I presume you can do, and so on. And you just get, actually that's the formula. That's basically capital lambda inverse B bar, but capital lambda is diagonal. So you get this. Okay? So far, nothing interesting here. But now let's look at the Krylov sequence. Well, what you're doing here is this: yk is the argument of this thing over this subspace here. But the subspace here is actually really simple. It starts with a vector b bar, and you keep multiplying by these diagonal matrices. So these are just different diagonal matrices, and what that says is that the ith component of y at the kth Krylov point is a polynomial pk times the eigenvalues times bi bar. Okay? So that's it. And therefore, we can actually say we have now a beautiful formula, not in practice, but for understanding. If you understand this, you will understand all of it, of how it works. It says this. It says that the kth polynomial, that's the polynomial that generates the kth iterate of the Krylov sequence, when applied to A and then multiplied by B. That's the argmin over all polynomials of degree less than k of this thing. Okay? That's a positive number. It's a weight. And now you look at this and you want to know what polynomials what polynomials can you do here? This thing of course will be this thing here. It can be negative. That's actually the whole point because of this thing. And so here it's lambda I times p of lambda I, and then minus p of lambda I. So in fact, this is p of lambda squared. We'll get to what this means in just a second here. Okay? So you can write this another way. It says that if you look at how close you are at the kth iterate to the maximum reduction you're going to get, that's f bar of yk minus f star. And that's the minimum of this. And now these are just writing it in different forms, so you start figuring out how you want to how to understand what happens. But don't worry, we're going to go over this on next Tuesday, which, as I mentioned earlier, will probably be tomorrow, next Tuesday. So this, if you simply work out what this is, you take out this thing here, and you end up with this. This is a generic polynomial here, whose degree is n here, because or a degree is less. Sorry, whose degree this degree is less than or equal to k, but it has the property that if you plug in, let's see, 0 in that polynomial, you're going to get 1. You're going to get 1. That's going to be this thing. That's the negative of this. So I can rewrite that this way, and you finally get to something like this, and it's quite beautiful. It goes like this. It says that if you want to know how close you are to the solution after k steps, you are exactly No inequalities here. You're exactly this. It says take bi bar squared. That's actually how, that's basically sort of like the, in fact, bi divided by lambda I is the solution or something like that. But it says what you want to do is you want to find, you look at all polynomials of degree k, and then this is sort of a weighted positive sum of q evaluated at those points. Okay, now, by the way, you're not supposed to be following all the details. It's just sort of the basic idea here. And then, so what it comes down to is this. It says if there is a polynomial of degree k, a monic polynomial, sorry, not monic, but one that at 0 is 1, so constant coefficient 1, that's small on the eigenvalues of a, then it means you get a good approximation. Okay? And this tells you everything. So it works like this. It says, for example, if the eigenvalues of a are sort of all over the place, but let's just see some pictures about how this works, and then we'll quit for today. Let's draw, here's 0, and let's draw some eigenvalues. So if the eigenvalues look like that, and you have to have a polynomial that starts at 1, and if I asked you sort of what's the best degree 1 polynomial, I mean, it means, best means it should be small near these points. It's going to be something that looks like this, right? Okay? But if I ask what's the best degree 2 polynomial, you're going to make something that kind of, let me just try. It's going to, it's going to be a quadratic, and it's going to kind of look like that. Everybody got that? And look at this. On here, you're sort of, the polynomial is not too, it's pretty small. So what that says, this thing then predicts that the second, if that were your spectrum, the second step in the Krylov sequence is going to actually have really low error, right? Everybody see this? So it's very, and by the way, if it were exactly clustered, in other words, if A had exactly like 2 eigenvalues, x2 will be the solution. Okay? That's not that interesting, but it's a fact. Everybody see why? Because then I can find a degree 2 polynomial that will go exactly between, that will just go right through and give you 0, and you get the answer. Does this make sense? Okay, so this is, this is just your first exposure to it. We're going to quit here, and in the next lecture, which like I said will probably be taped ahead sometime tomorrow, we'll go on and look at all the implications. That's it.